Good afternoon, everyone.
Good afternoon.
Good afternoon.
Let me share my screen with everyone. And can you all see my screen?
Yep.
Okay, perfect. So let's see. Okay, so we got 2 class periods left, and we're obviously finishing up functional languages over the next 2 class periods. So today we're going to finish up with showing you how to construct quicksorts. So I've been trying to give you some examples, showing you how you can construct programs using either tail recursion or an inductive construction. And then I want to show you a more beefier scheme program that manipulates a deterministic finite automata, because I know that programs you're writing seem complicated in the homework assignment, but they're still relatively simple, obviously, to the kind of bigger programs you might have to write in the real world. And finally, I switched higher order functions and evaluation order. And the reason I did that is because you have 2 questions, at least 2 questions on the homework assignment that cover higher order functions, and you have only 1 question on the homework assignment that covers evaluation order. So let's actually take a quick look at the homework assignments for a moment.
Yeah, problem 7 is melting my brain currently.
Okay, yep, so that one is the one. This problem right here, we don't get to until Tuesday. So I know y'all want, I think what I'll do so you can hand in stuff early is break this problem off so that you can still get an early submission without having to do this problem. Because I don't plan to get to this problem until Tuesday, okay? And I don't want to preempt the possibility of you getting 10 extra credit points by handing in 2 days early. So what I'm going to do is break this one problem off into a 3rd submission. Does that sound reasonable?
Yeah, that makes sense to me. That'd be cool.
Anyone really opposed to that? Okay. So what you will be able to do after today is question 6, where you're flattening a tree. Basically, you're going through a tree and printing out all of its leaves. In this case, 11, 9, 5, 1, 7, 10, 4, and 17. It's called flattening a tree. And I want you to do it with higher order functions. And same thing, 5, the filter function is effectively a higher order function too. It's a variation on the reduce operator that we'll go over today. So we will do that. In fact, to make sure we get to it, I will do that first before I even go over the higher order functions. I'll go over the higher order functions before I go over the deterministic finite automata simulation. Okay, the other thing I want to point out, our final exam, Wednesday, May 5th, and I haven't had a chance to come up with the questions for it yet, but the sample exam you see is a pretty good example of what you're likely to get, which is probably a Python coding question, a scheme coding question, but no coding questions for either GUIs or for concurrency. Instead, just multiple choice, multiple answer, fill in the blank, and that kind of thing for graphical user interfaces and concurrency. So expect, as I said, simple programming problems for Python and Scheme, but nothing for concurrency or GUIs as far as having to write code. And I will try to—
Dr. Vanderzanden?
Yeah, yes, go ahead.
When you say simple, I'll be honest, to me, none of the scheme stuff is simple. So I'd just like to clarify that. Is it something like the minimum function?
It would be something like the minimum function, because I figure that you have written a minimum function and an average function. So you could presumably do some kind of template matching. I know it probably takes you a while, so it wouldn't probably be
like I can on the homework. I was able to get the first part of the homework. It just definitely takes me a while to wrap my head around, and I worry about doing that in the constraint of an exam time, right?
So two things. I will make sure if there is a scheme problem, it's not worth a lot of points. And two, don't attempt it to the end.
I can do that. Thank you.
So I'll do both. The scheme problem, if there is one, will not be worth a tremendous amount of points.
Scheme is weird. Min took me a long time to write, and then I just threw a guess at merge sort and wrote it in like 10 minutes. It's crazy how
it can. I understand how it can either go easily or go forever. The one advantage on the final exam is you won't be able to have access to a scheme interpreter. So you won't know if you're actually screwing it up or not. Meaning you won't be bogging down on thinking, oh, I've got syntax errors or other stuff.
Ignorance is bliss. I'll take it.
Yes, that's right. So in fact, I will commit to the scheme problem being worth no more than 5 points on the final. So now that doesn't mean that I won't give you problems where you might have to trace it and tell me what the answer is. That's different, okay? What I'm committing to is no more than 5 points for writing a scheme program. But there's going to be questions where you might have to read code or tell me advantages of functional languages or disadvantages or things like that. And if you look at the sample exams and you look at the final, you can see example questions. So this was from functions, functional programming. That's a question. This technique used by functional language interpreters. So I can certainly ask those kinds of questions, and I won't be limiting myself to 5 points for those because functional languages represent 1/4 of the final portion of the course. So you can roughly expect that GUIs will be worth 25% of the final exam. Python will be worth 25% on the final exam. Scheme will be worth 20, or functional programming in general, 25%, and concurrent programming roughly 25%. So, so I'll get a review guide up sometime this weekend. As I said, you have the option of taking it in person or by Canvas. So it'll be, again, an online Canvas exam. But if you want to take it by hand in the classroom, that's fine. Just since I think that option will only be taken by a couple individuals at most, please send me an email indicating you plan to show up that day, and I'll just have a paper version of the exam ready for you. And it will be open note, open book. So any other questions about the final?
Yeah, so like if it's open note, open book in person, how would that work from like the perspective of having our computer?
So I would basically allow you to use your computer because I can monitor you. I can sit behind you in the classroom and see what you're doing.
Okay, cool.
So it's
and that would mean, I mean, I assume no lockdown browser. If you're in person, you're free to browse the provided resources just on the open web, right?
Right, because there's a way for me to say it's being proctored. So that's your option. If you want to come in and then, like I said, I'll be at the behind y'all so I can easily see your screens. So that to me assures me that you're not cheating. So yep, if you don't want to have to use a lockdown browser, come to class, come to the exam, but shoot me an email so that I have an idea of how many people to expect. Other questions? Okay, in that case, let's take so I was telling you last time that there's two ways to construct, well, there's more ways than two to construct a functional program, but these are the two I think are most useful for this course. So using tail recursion by essentially always processing the first element in the list and then using continuation arguments to keep partial results so that by the time you get to the base case, which is the end of the list, you have your result and you simply pass it back. So I say that's akin to pre-processing the list because you start by doing some processing on the first element of the list, and then you pass a continuation argument and the remainder of the list to the recursive function. And then the inductive construction is exactly the opposite. Effectively, you end up by processing the last element of the list first when you get down near to the base case. And then when you get back from the recursive call, that's when you combine the first element in the list with whatever the result was returned by the recursive call. So it's post-processing because you're doing your processing of that first element after the recursive call returns. So we went over the factorial and sum of numbers, which I'm not going to do again. So instead, I'm going to show you quicksort, which is the beefiest of our examples. And turns out that what we are concerned with primarily is the partition of the list. So if you don't remember what quicksort does, it effectively, if you have a list, like say 3, 8, 1, 9, 4, 5, 8, 7, it takes the first element as the pivot, and anything less than the pivot, well, let's add 2. So in this case, 1 and 2 go into one array, the so-called lower array or lesser array, and everything greater than the pivot, in this case, 8, 9, 4, 5, 8, and 7, go into the so-called greater array. So in fact, here just a second. So you have, say, 3, 8, 2, 1, 5, 6, 7. You would basically have 2 and 1 in one array. Then that's the lesser array. Then you'd have 3 in the middle. Then you'd have your greater array consisting of 8, 5, 6, and 7. And you recursively sort the lesser and greater array. So that's quicksort in a nutshell. You take a pivot, you divide the list into 2 lists, one with all elements less than the pivot, this one with all elements greater than the pivot. Then you basically finalize it by sorting the lesser list, putting the pivot in the middle, and sorting the greater list. Okay, so we're defining a function. This is a helper function. Notice in this case, I didn't use a letrec. I'm actually doing it outside of the qsort function. So this is a case where I'm actually setting up a helper function that is in the global namespace. And it is taking a pivot and a list. So with the inductive construction, we start with what happens with a null list. And a null list is very easy. We return it. In fact, sorry, we don't return the null list. Instead, we return 2 empty lists denoting the lesser and the greater list. So that partitions, it's easy to partition an empty list. If it's not an empty list, then what we do is we partition the remainder of the list using the pivot. So when we get back from qsort partition, we're going to have two lists, one with all the lesser elements and one with all the greater elements. So let me show you. So let's say that I had a list. Let's go back here. Maybe, no. Okay, let's go back here. Come on, there we go. So basically what qpartition is doing is you're coming in with a pivot. So this in this case would be 3, and your list would be 8, 2, 1, 5, 6, and 7. So what the inductive construction is doing is saying, let's first partition the cdr of the list and set aside the car for the time being. So when the partition comes back, 2 and 1 will be on one list, although not necessarily in that order, and 5, 6, and 7 will be on the other list. So qpartition is returning two lists, one with all elements less than the pivot and one with all elements greater than the pivot. So obviously 8 should be added to this list because 8 is greater than 3. So that's what's going on here, is that we first, with this one right here, partition the remainder of the list. That gives us two lists. And notice we did a cons, so we can get the lesser list by carring the result and the greater list by qdring the result. Okay, actually, let me get back to the, so the lesser list by carring the result, qdr by, I'm sorry, greater list is the qdr. And then we check to see if we deal with the car. So if the car is less than the pivot, we're going to add that element to the lesser list. So we cons the car onto the lesser list, and we return a cons pair now consisting of the new lesser list, which is let's see, this right here is the new lesser list. And we're consing that with the greater list. If it's not less than, then you can see anything greater than or equal goes onto the greater list. So we cons the item onto the head of the greater list and cons that new greater list with the lesser list. So when we're done, we're going to come out with a partition of that list. Okay, so we can show that, maybe. Okay, so let's actually copy that. And let's go into Hydra. Okay, and let's create qsort.scm. And unfortunately, VI tries to be helpful by turning everything into a comment, which I don't want. Let's check, okay. So let's try to load this then. Okay, so we'll load this. And let's try to do the partition. So first let's trace it. And it is named qsort partition. So let's do qsort partition on that list. So it's 3, 8, 2, 1, 5, 6, 7. Okay, so you can see what's going on. So we start, and the first thing we do is we call partition on the smaller list. And you can see we keep working down until we get an empty list, at which point we return this list that has 2 empty lists. And that's what comes back from the partition of this empty list. So now we're trying to partition 7, and since 7 is greater than 3, it goes on to the greater list. And it comes back here, and 6 is greater than 3, so it also goes on the greater list. That's what's being returned from qsort partition of 6 and 7. So this now comes back to qsort partition of 5, 6, and 7. And again, 5 is greater than 3, so it goes onto the greater list. And that comes back up to this qsort partition of 1, 5, and 3. 1 is less than 3, so for the first time we end up with something on the lesser list. Comes back up here where we're now looking at 2, and 2 is less than 3, so it ends up on the lesser list. And finally, we have 8, and 8 ends up on the greater list right here, and that's what ends up getting returned out of our partition. Now, if you're doing a trace, this looks funny, because you see this one looks like a list, and this one doesn't. But we still actually have, this is still a cons pair, even though it doesn't look like a cons pair. You just have to get used to the fact that this is correct. This is one of our lists, and 5, 6, and 7 is our other list, even though it doesn't have a left parentheses in front of it. It's just list way of showing the 2. Okay, so questions about this partition. Okay, so in that case, let's go and look at the tail recursion version. Remember, tail recursion is going to need some continuation arguments. So in this case, in addition to the pivot and the list, we're going to be constructing our 2 lists as we go along. So L1 is the lesser list, L2 is the greater list, and we're building them both up as we move along. So we're always going to take the first element and immediately add it to the appropriate list. So if we've gotten down to the empty list, we simply cons our 2 lists together and return them. Otherwise, we get the first element and ask if that first element is less than the pivot. If it is, then it is going to be added to the lesser list right here. And if it's greater than or equal, it will get added to the greater than or equal to list. So if it's less than the pivot, we call qsort partition passing the pivot. We've reduced the list by 1 element, so we pass the cdr, and we prepend the first element of the list to the lesser list. If it's greater than or equal to the pivot, same thing, except that we add the element, we prepend it to the front of the greater list. So if we take a look at this one, let's call it qtail.scm. Get rid of those darn comments again. Write it, load it. And again, we'll do the qsort partition after we trace it. And it didn't like that, because I didn't pass in the right number of arguments. Okay, so I need to pass in 2 empty lists because initially the 2 empty lists, the lists are empty. Okay, so here you see that we start by processing the 8. 8 is greater than 3, so it goes on the greater list, and we pass the remainder of the list recursively. 2 is now the first element of the list, so it gets added to the lesser list, and we pass the rest of the list to the recursive function. 1 is less than 3, so it gets added to the lesser list. And you'll see then 5 gets added to the greater list, and then 6 gets added to the greater list, and then 7 gets added to the greater list. And so now we're done because we have the empty list, and this is our final result. And you'll notice this was our final result with the inductive approach. You'll notice that the lists are reversed. So here it's 2, 1, here it's 1, 2, here it's 8, 5, 6, 7, 8, 5, 6, 7, but in reverse. And the reason for that is because of the order in which they're processing the list. The tail recursive version is starting from the front of the list. The inductive version is starting from the end of the list. That's all that is different. And then to put it all together, it actually doesn't matter for the final result which version we use. Here I've used the tail recursive version. So I define qsort. If it's null, so if I'm giving an empty list, I simply return an empty list. Otherwise, I do exactly what I told you. I partition the list into 2 pieces, and the car of the list will be the pivot. Get the result, assign the car of the result to the lesser list, the cdr to the greater list, and then just as I showed you in the introduction, I append together the 3 lists. I qsort the lesser list, create a list out of the pivot, qsort the greater list, and that gives me my result. So just to show it to you, to kind of close the circle, we will add that qsort there. We will load it. And call qsort, and now 3 is part of the list that we're sorting. And voila, it is in sorted order. Okay, so that obviously is the beefiest of the 3 examples. As I said, on the homework assignment, unless I tell you you have to use one approach or the other, you are free to use whichever approach is easiest for you. I will tell you that the tail recursion approach is more like what you do in imperative programming. So I suspect for most of you that you will find the tail construction a little easier to deal with. But for some of those of you who are more mathematically oriented, you may find that the inductive approach is your preferred construction style. So any questions about what we've gone over as far as constructing these programs? Okay. In that case, let's go and look at higher order functions. And talk about them. So basically, a higher order function is one that takes a function as an argument and applies it to the remaining parameters, or it returns a function as a result. So it's kind of like a meta function in some case, in some sense. And you're used to actually dealing sometimes with a version of higher order functions in C, where you have to pass in a comparison function to something like qsort. So here in C, I am comparing two ints and returning their difference. And then I'm sorting this temperatures array. And in C, there's this qsort command, and I pass it this function that can be used to compare the elements of temperature. So this is a little bit in the spirit of a higher order function, although not really what we mean when we're talking about higher order functions in Lisp. But I just wanted to show you that you do have some experience with passing functions as arguments to other functions. Okay, but what we really care about is two big functions, map and reduce, which are used extensively in the data science world these days. So a map function takes a function and applies that function to each, pairwise to each element in the remaining list. So here we have map. It takes the multiplication operator. It's going to apply it to these two lists. So it'll apply it to 2 and 3, getting 6. It will apply it to 4 and 5 to get 20. And it will apply it to 6 and 7 to get 42. So it's taking this function and applying it pairwise to each elements on these lists. And of course, these lists should be the same size. And I did not try this, but my guess is you can have more than 2 lists. Let's just give it a try quickly. So it worked just fine with 3 lists. 3 times 4 is 12, times minus 2 is minus 24, gives you that result. 6 times 1 is 6, times 8 is 48, and so on. So in fact, this map function can be applied to as many arguments as you want. Okay? And then the second common function is reduce. And you use that to reduce something to a list to a final result. So for example, I might want to add, I'm sorry, in this case, multiply all the elements of this list. So 2 times 4 is 8, times 6 is 48. So I reduce a list of values to a single value. Another example, min. I might want to find the minimum element of the list, and that is effectively a reduce function. So what I do with the reduce function, it takes a function that I am going to apply to a result and the first element in the sequence. So for example, fold for 4 and 6 is going to return 24, and then I'll multiply that result by 2 to get 48. And I normally have to start with an initial value. This is comparable to initializing a function, I'm sorry, a value to an initial value. In fact, let me do this first. No, actually, let me go to my notes first. So what reduce is looks something like this imperatively. So you first assign your result, you initialize it to some value, which we call the identity value. Then you essentially run through every element in the list and you apply that element in the list with the function that you're given to the value you have so far, to your result. So essentially what reduce is doing, starting with some initial value, running through a list, and applying the function to the result thus far and the next element in the list. Okay, so that is what we're doing here. This is our identity value in our sequence. So if the sequence is null, we return our identity value. That's kind of the base case. So here I am using an inductive construction for the reduce function. If the sequence is not null, I apply the function to the car of the sequence, so the first element in the sequence, and the result that I obtained by applying fold or the reduce operator to the remainder of the sequence. So it's just, it's simple. I think the best way to show it is, I'm again going to trace it for you. So I will create a fold, call it reduce.scm. And we will run it. So we want to do fold, and we'll use plus 0, and we're going to sum the list 3, 8, 10, 12, and 15. Okay, so you see that what happens is we start and we're going to add 3 to the result of this list. So we call fold first on the cdr of the list. We keep calling it on the cdr of the list until we get down to the empty list, at which point we return 0. So then we return 0 up to this function, add 15 to 0, and it returns 15 as the result. So 15 gets returned here, and we add 12 to 15 to get 27. So this fold right here is returning 27. So 27 is the result of calling fold on this function. I'm sorry, on this value. We add 10 to it to get 37. So we would then return 37 to this function, add 8 to it to get 45, so on and so forth. So effectively, we start by adding elements from the back of the list rather than the beginning of the list, but it is folding them into a single value. Okay, and actually before I give you this example, let me give you a real world example of how this works with big data science. So in big data science, what you might have is a bunch of sensor files, okay? Sensor readings. So perhaps what you have is a sensor file from 3/1/21. And it has a bunch of measurements from Knoxville, has some from Nashville, and they're all may be interspersed. They may not be all together. Of course, I'm probably going to misspell Chattanooga. Okay, same thing. Then there's a sensor file for 3/2/21 and a sensor file for 3/3/21 all the way up to 3/31/21. And what we want to do is find the maximum temperature in each city for the month of March. So the first thing that we want to do is for each file, we want to get a single value for Knoxville, a single value for Nashville, and a single value for Chattanooga. And we want to apply that to every single one of these files. So what we're going to do first effectively is a map operation on all 31 files. And the function that we're applying to each one is to find the minimum. So we have a function that finds minimum temperature for each city. In each file. So what we do is we apply the map function the map function, passing it this function for each of the 31 files. And that's going to give us 31 results. So at the end, we're going to have 31 results where we have a result for Knoxville from the 1st of March. Maybe the temperature there was 36, the high temperature there was 36. Maybe Nashville, the high temperature there for that day might have been 38. So that's on 3/1. Maybe for 3/2, Kville was 42, Nashville was 45, ... down to 3/31, Kville was maybe 64, maybe Nashville was 62. So now what we have is 31 files, and we effectively want to apply a reduce operation that's going to return a single value for each city. So we want in this case, 64 is the highest value for Knoxville of the three you see, and 62 is the highest for Nashville. So in effect, we first did a map to get a single temperature, high temperature for each city, for each file. And that gave us, we did that once for each of our 31 files. And then we did a reduce over the 31 files to get a maximum temperature for each city. So that's kind of the idea with how you're using MapReduce with big data science. And I'm not a data science person, so this is just an example I have seen and it appealed to me. So another example of MapReduce that is more mathematically oriented let's see, is one with matrix multiplication. So we want to multiply this row by this column and then get its sum. It's often called a dot product, that you take one row, multiply it by a column, and take the sum of the product. So we want to multiply 1 by 17, multiply 2 by 5, 10 by 3, 12 by 11, 17 by 8, and then we want to sum those results together. And that's a MapReduce thing. So we first apply map to the row and the column. So row and column. And when we do that, you can see here we get 1 times 17, 2 times 5, 10 times 3, 12 times 11, 17 times 8. And those evaluate to 17, 10, 30, 132, and 136. Then we fold that result by applying plus and 0 to that result, and that gives us 325. So that's another example. This is a very succinct way of expressing matrix multiplication, or dot product if you prefer to call it dot product. Okay, so that is 2 examples of higher order functions. The third one that we're going to talk about is something called curring. And curring is where we replace one of a function's arguments with a constant value and return one fewer argument. So it's good for creating simpler functions. So as an example, we have a function that we want to add a and b. But in fact, a is supposed to be a constant of our choosing. So we pass in this value that we want to be a constant, and it returns a function in which the first operand has been converted to a constant. So for example, if we call curry plus 3, what that does is it produces a new function, lambda b, that adds 3 and b. So curry plus is returning this function right here. So this function right here returns this function right here. And now 4 is passed as an argument to b, and we get 7. Okay, so that's kind of a silly little example where we're simply replacing one of the operands in a sum with a addition. But curring also works really well for simplifying functions and replacing them with something that is a more meaningful name to a user. So for example, I can create a, I can call fold with plus 0 and L to add up the elements of L. So this will start with the sum of 0, apply plus to that list, and add all the elements of the list together. But that's not a very informative name for what's going on, which is it's summing that list. Okay, total is probably not a great name either. Maybe I should have named it sum list. But what I'm doing here is curring out by defining total to be a single argument function that takes a list, and it actually applies the fold function to that list with the plus operator and 0. What I'm doing is curring out 2 arguments, the plus operator and the identity value. I'm making them constant values. And in return, I'm getting a more meaningful name for the operation. Now, again, I didn't choose a very good name with total. I wish I called it, in fact, it's easy. I could have just called it sum list. That's a much more meaningful name. Notice now I can just call sum list, and I don't have to worry about calling the fold function with the right operator and the right identity value. And in fact, if you look at Python, remember earlier this semester, we saw that map was still a built-in function in Python, but the reduce function had been moved off into a Python library. And the reason reduce had been moved off to a Python library was precisely because this kind of form is not particularly meaningful to someone looking at code, whereas this is. So what the Python developers did was actually effectively developed a whole bunch of, took a lot of common operations like min, max, sum, and they curried them to produce names like sum, min, max that you could apply directly to a list rather than having to call the reduce operator. So in fact, when Python developers moved reduce off to a library, the reason they did it was because they had curried away the function and the identity value and instead created a whole bunch of common operations that people used to create using the reduce operation. So that's a real world example. The Python developers actually did use this currying operation so that they could relegate the reduce operation to a library. Now the map operation, they couldn't do that. The map operation is still a built-in operation in Python. And if I'm not mistaken, Python also has a filter operation somewhat similar to the one that you're implementing in the homework assignment. And filter is I guess it's not really, it's kind of like reduce. So going to the homework assignment, so filter is a little bit like reduce in that it is applying this function to each of the values in the list. Where it differs is there is no identity element because the function returns either true or false. And if the function returns true, you include the result in the final list. And if it doesn't, it's omitted from the final list. So it's kind of like it's a special form of a reduce operator that you're applying. And again, Python has a built-in version of the filter function. So filter, map, reduce. Those are three very handy higher order operations that are very common in data science. So the filter function obviously is a pretty common one in data science too, as far as being able to filter out parts of a file. And then currying is just a useful technique. So currying's a little different. Map, filter, and reduce are very helpful functions. Currying is actually more of a technique for replacing one or more arguments with constants. So you kind of get a more syntactic sugar version of something that's going to be a more meaningful operation to a user. So any questions about any of the stuff I've covered?
I have a question about the term syntactic sugar. What does that mean?
Good question. So in the programming language community, people refer to syntactic sugar as something that makes something easier to read. It doesn't change the meaning of it, but it makes it easier to read, makes it easier to swallow. So that if you're wondering where it comes from, it's like a teaspoon of sugar makes the medicine go down.
I see. That's cute.
Uh-huh. So you often hear the word syntactic sugar when, so the other thing is you will often hear people criticize functional programming and saying, well, it's difficult to understand. Like you all are probably wrestling with this pre-order form of calling functions and operators. It's not natural to put the operator first. So functional programming advocates just scoff and say, oh, it's just syntactic sugar that you get to put operators in the middle. It's no big deal whether they go first or in the middle. It's just syntactic sugar. But to mere mortals, syntactic sugar makes programming a lot easier. A lot of what makes Java so much easier than C++ is that so-called syntactic sugar. So it's, yeah, that's what it is. Just making stuff easier to read. Other questions? Okay. So we got 20 minutes left, and I realized that what I can do with the 20 minutes is show you how to do that final homework problem so that if you want to do it over the weekend, you can do it over the weekend. So
that would be amazing. I spent like 4 hours on it last night and just can't wrap my head around it.
Gotcha. Okay. So you all can see this. This is problem 7. You're writing a stream to lazily create a list of Fibonacci numbers. And you may not remember this, but in Python, do you remember the concept of generator functions from Python?
Yes.
This is something that is ripped off from functional languages. So functional languages call them streams, and Python calls them generator functions, which are probably a little easier way of thinking of it. So this concept that you're doing in problem 7 is similar to Python's notion of a generator function. So let's just start with a couple slides and then we'll come back to this. I think I may have to open up something. Yeah, I'm going to have to open up just to, whoops, I don't want a new presentation. Okay. So, don't think we really need, okay, so we do need a couple definitions. So there's 2 ways of evaluating arguments when you invoke a function. What's called applicative order means you evaluate all the function arguments before you invoke the functions. And this is what happens in imperative languages. And then there's normal order, which doesn't evaluate an argument until you need it. It's kind of just in time. And conditional and conditional or are examples of normal order evaluation. In conditional and, you evaluate the left side of the and if it's true, you don't evaluate the right-hand side. So that's an example of normal order evaluation. Okay, and as you can see here, we often use it to good effect in an imperative language because we'll first check to see whether the dividend is 0. And only if the dividend is not 0 do we do the division. And if we did applicative evaluation, this would give us an error because we would try to divide x by 0. But if we use normal order evaluation, where we don't evaluate an argument until we need it, we would never evaluate the second argument because the first argument evaluates to false. Okay, and there's a few things in scheme that are normal order. The con statement is a normal order because it evaluates the arguments in a conditional in the order in which they are presented. So we'll go over this other stuff on Monday. I want to get to the generator function. So by default, scheme uses applicative order. It evaluates everything eagerly. And what we would like to do is sometimes not evaluate something eagerly, but delay evaluation of it. And so Lisp, and the reason we do it is so that we can create a generator function where we only generate one element of a list at a time, and then we delay the computation. So let me actually quickly flip back. This may help. I'm going to quickly flip back to the Python notes for a moment. And I think it is day 1. Yep, generator functions. By the way, big hint, this could very well help you for the Lisp assignment. So here was how we did a generator function for the Fibonacci numbers in Python. So we immediately yielded 1 and then it stopped. And when it resumed execution, it yielded a second 1 and it stopped. Then we set current and previous to 1 and 1. We said while true, so we're in an infinite loop. We set current and previous to new values. And then we yielded the next value, which returned it, and again, paused the function. Okay, so we're trying to do the same thing right now in Lisp. What we're trying to do is yield up one element of the Fibonacci sequence at a time and then pause it. Okay, and we can do that with these delay and force constructs. So we start, and this is just a very simple example. We assign this expression a plus 10 to expression, but rather than evaluating it immediately, we pass the expression to delay. And that says basically, don't evaluate the expression just yet. Evaluate it later when we force the evaluation. So then we define a to be 15. We force the evaluation of the expression and it results in 25. Okay, so this is your example that I don't want to do the homework problem for you. So instead, we're going to do the natural numbers. We're going to generate the natural numbers one at a time. So the natural numbers start at 1. So 1, 2, 3, 4, 5, so on and so forth. So a stream is just, we're generating a so-called infinite list of elements. And in this case, we're generating an infinite list of the natural numbers, one at a time. So it's going to be like a generator function in Python, but in a slightly different way. So we are again going to recursively generate this list. So we're going to name our list next. I'm sorry, our function next. And it's going to take n, and it's going to generate the next natural number. So what we're doing is we're consing n onto or at the head of the remainder of the list. So the remainder of the list is all natural numbers n plus 1 or greater, but we can't generate that because it's an infinite list. So we want to, in effect, yield. So yield is not exactly comparable to delay because yield actually was returning a result. But whereas here, what we're doing is we're actually creating a list. So that's where things are a little bit different. In Python, the yield command is a bit like a return statement that returns a result at a time. Instead, what we're doing in Lisp is we're constructing a list. But we're constructing the list one element at a time. So each invocation of next effectively enumerates the next element of the list. And it does it by consing the n onto the rest of the list. So you can kind of think of the yield as being the con statement. It is consing n and then saying, okay, delay the rest of the evaluation until later. And the rest of the evaluation will call next with n+1. And then we start the stream by calling it with 1 because that's the first one that we want to generate. Okay, so let's look at what happens when we do this in Gambit. So I'm going to call it natural.scm. So hopefully you can see that unlike my other cases, there's no base case here. If I run this without the delay statement, I'm going to get an infinite recursion. It's never going to stop. Okay, so the delay statement is going to keep, whoops. So I'm going to load natural. Okay, unbound variable next. That's because it's natural. Should be bound. Second. Let me check something. Okay, let's see. Yes. Okay, so if you take the car of naturals, it works because when we start executing next, it immediately conses n onto this function. So immediately the first element of the function is available. So when it effectively next one returns, what we have effectively is 1 const with this delay of natural. I'm sorry, I think it's next. Plus n1. So when we say car, we get this 1. But if I say catter, which is really saying I want the car of the cooter, well, the cooter is this delay. So I'm trying to take the car of delay, which doesn't work out so well because that's undefined. That's why when I tried to take the car of the cooter, it gave me an error because this is the so-called promise. It's not actually getting evaluated. So what I need to do is force the evaluation of that. So what I could have done instead, I can say, take the, so we start by taking the cooter of the naturals. And what that's going to do is it's going to give me this promise element. So now what I need to do is force that evaluation. Okay, and that gets me 2. Which, so I could have actually then taken the car of that. And it would have worked. So again, what that delay does is it immediately made the first element available, so I could car it, and it left what in effect is a generator function for the remainder of it. And when you take the cdr, you get your hands on this generator function, which you now have to force execution on before you can take the car, which is what I did here. There's a force on the cdr. So what's going on here is they actually tried to create a function that would do that for us, that it would force the next natural number to be generated. So it takes this stream object and it calls force on the cdr of that stream, and that gives you back a list that has one element on it. So when you call this force, what you get back from this function is what you saw right here. It gave me one new element in the list, and then it gave me a so-called generator or promise object for the next, or for the remainder of the list. So they called that function tail, and that way tail could always force the next element to get generated. So tail of naturals forces the second element to get generated. Calling tail twice forces 2 elements to get generated. So if we go and define tail, we can now say, okay, tail of the naturals operator is not a procedure. Just a second. Not. One second.
I think you might still need the car.
You may be right. That's what I was going to try. I was thinking it could just show you a generator. So I'm going to just do this now. See if that works. Yep, that works. So apparently you have to apply the car in order to make it. And that did. So you're going to have to play with it, obviously, because this is not. So there,
this is what was confusing me.
Bingo. Yeah, I can see why it's confusing you.
So the.
Because you just, in fact, it turns out you just want to take the car of the tail.
Of the tail. So you need to recursively get tail to get whatever element you want.
That's right. So.
And I'm struggling with that for the Fibonacci numbers.
Okay.
Like
then
writing a recursive tail function, essentially.
Okay. Let's then, it's because I want to let the rest of the class go, so we can talk about that offline. So if you could just stick around for a couple minutes, we can talk about it.
And I'm sure you're feeling kind of icky with that. I don't want to take up any of your time if you're.
No, I can actually, well, I have a history of having to lecture with fevers. So I'm actually very good at managing it.
All right, I wouldn't want to break tradition then. I can stick around.
Okay, so I'm going to let the rest of you go. And on Tuesday, I'll go over this a bit more to try to help you with the Fibonacci numbers. If you want to stick around and participate in the discussion I'm going to have, that's fine. Otherwise, y'all are free to leave, and I will see you all on Tuesday. Whoops, I want to end the meeting.
So